Hello everyone. So this is the second demo lecture for the GATE online classes. Okay, and we'll be discussing the topic for discussion of today is auto transformers. Okay, it is one of the important topics and it is one of the easier topics also. Okay, if you understand the basic concept of how a two-winding transformer is converted to an auto transformers, okay, then it is very easy for you to handle questions that usually come in GATE particularly. Okay, and it will also give you an edge to solve the other questions and to take more time for other questions, because in this topic the questions usually are not of that much means not of that much time taking. Okay, if you know the formula, if you know the concept really well, you can just click the question and you can just move on to the next one, which requires more time, and it will give you an edge in the exam, during the exam, over the people. Okay, so without wasting much time, let's get started. So this lecture will be in parts. The first part will be dealing with the Lenz law and the dot convention, because it is important to understand both the two-winding transformer and the auto transformer. Okay, that is why we'll be starting with this, and then from after that we'll be dealing with the auto transformer part, all the derivations, the kVA advantage, copper saving, all its merits, demerits, its comparison with the two-winding transformers, and all the related formulas we'll be dealing with in part 2. And then I'll be giving a list of shortcuts, okay, that will be very handy, and those shortcuts you can directly apply in the questions, and you won't be wasting your time for the conventional method that usually auto transformer questions indulge in, right? So let's get started. So the first topic is Lenz law and the dot convention, right? So Lenz law, in layman language, you can say that effect opposes the cause. I won't be writing the definition and all those things, those are not relevant for GATE exam. Okay, so this is the thing that is important, and that's why only this is written, that is effect opposes the cause. Now whatever effect whatever effect it is, it will always opposes the cause. In induction machine, like I told you in the previous lecture, rotor induction machine, the relative speed was the cause. Okay, so the effect that is the rotation of the rotor has to reduce the relative speed. Okay, in the there also Lenz law was applying. Here Lenz law, the effect and cause are in terms of flux. Okay, so as you can see, this is one transformer, this is another transformer. The basic difference is the sense of winding only, the sense of winding of the secondary, right? Here the sense of winding is like this, and here the sense of winding is like this. Both the senses of windings are different. I made these two cases so that you can understand that it's not only the dot convention, but also the sense of windings which determines how the current will flow in the secondary side of the transformer, or on the side on which the load is connected. Okay, right? And in transformer we'll be dealing with we won't be saying primary and secondary sides, because there is no definition of a particular transformer saying that this is primary side and this is secondary side. Okay, there is a high voltage side and there is a low voltage side. Okay, here I am not considering voltage, that's why I'll be talking about primary and secondary. Okay, but in real transformers, if you're talking if you are taking real examples, then in that cases do not use the terminology primary and secondary, just use high voltage and low voltage, right? So let us start. If we connect a voltage, okay, if we connect a voltage here, right, a voltage excitation is given, a sinusoidal excitation is given, and a current is flowing in this direction, that is from left to right. Okay, so by right hand screw rule, and also one more important thing, all the rules you should be clear before coming to this lecture, because right hand screw rule is very much important in determining the direction of the magnetic flux and the current. Okay, it is very simple. There are two things only. You have to make a fist. Okay, you just have to consider a current carrying wire or a rod is there in your hand. Okay, the curling of fingers represents the direction of current if there is a winding, and the thumb will represent direction of the magnetic flux. Okay, so if the direction of current is from left to right, here left to right is here. Okay, so what will be the direction of magnetic flux? It will be from downward to upwards. Okay, it will be like this, phi 1. This is the cause. Okay, because we have applied a voltage here, and because of that voltage a current flows in the winding. Because of that current a flux is created, that is phi 1. Now in this winding also, because of this flux a voltage will be induced. Okay, voltage will be induced. That voltage will create a current which in turn will produce a flux which will oppose this flux. Okay, so the effect will be another flux which will be in this direction opposing the flux phi 1. That this flux is known as phi 2. Okay, right. So this phi 2, if the direction of phi 2 is from downwards to upwards, from right to left, okay, in this direction, so what will be the direction of current flowing in this winding? What will be the direction of current? The direction of current will be here, like this. Okay, you can see it by yourself also. Just apply the right hand rule, in which the curling of fingers will give you the direction of current, and the thumb will give you the right hand screw rule. So take your right hand, okay, and the thumb will give you the direction of the flux, right? So this will be a direction, that is the current is coming out of the C port and going inside of the D port. Okay, this is the here we'll apply the load, and the polarity will be like this, right? And okay, so this case is done. So now let us take the example of this case. In this case also the same flux will be in this direction. Okay, flux will be in this direction. So now considering the sense of winding here, what will be the direction of current? Again the thumb will point upwards. Okay, we are talking about the secondary winding. The thumb will point upwards, so the curling of fingers will give the direction of current in this direction, right, from D, right? So if we apply a load here, the polarity will be like this. So the sense of winding is important in terms of the polarity that is induced in the other side of the transformer. Okay, so you have to keep in mind the sense of polarity also as far as the induced voltage polarities are considered. Okay, so that is what we have done here. And also one more thing, like in network theory also you might have studied, if these are the two inductors, okay, and there's a dot convention here, this is a dot convention, right? So and a current is flowing. So if this is plus polarity, so at particular instant of time the polarity which is at this particular dot will be same at this particular dot, okay, with the principle of mutual induction. So that is what it is here. See here the polarity of dot was plus. Okay, so the dot convention, according to dot convention, the dot will come here because the polarity plus is here. Okay, similarly this plus is here and the dot will come here because the positive polarity is here. The dot won't be coming here. Okay, because for the given dot convention the instantaneous polarities are always same as written in the second part. Okay, depending upon the sense of winding the dot polarities may change. That I have already shown you with the example 1 and 2. Okay, now and also one more observation that is very important, for which I took up this Lenz law case, was that if you see then for Lenz law to be applicable in a transformer, okay, if current is entering into the dot in one terminal, it has to exit the dot in other terminal. Okay, here also the current is entering into the dot in first terminal and it has to exit the dot in other terminal for Lenz law to be applicable, right? So this is the thumb rule that you need to remember, because we'll be using this rule a lot in the cases of two winding transformer and the auto transformer. Okay, so this is the observation that we have inferred from these two cases that we have studied right now. Okay, that is what I have written here. In a transformer, if the currents enter through the dot in primary winding, then it should leave the dot from secondary winding in order to satisfy the Lenz law, right? In order to satisfy the Lenz law. Now this is a small example in which only one dot is given, and you have to provide the dot conventions of all the other windings. Okay, so when I will be uploading the video, you can just comment it below. You can just comment it on which all are the ports on which the dots will come. Okay, just apply right hand screw rule. The flux which will be created by this winding, AB winding. Okay, the flux, all the other windings will be opposing that flux. Okay, all the other windings will be opposing that flux, and what will be the current direction that will produce that opposing flux will provide you the dot convention, right? So this is the question that you can solve, and you can answer in the comment, and you can comment in the comment box when I'll be uploading this video, right? So this is the basics, these are the basics of Lenz law that we need to know before considering the auto transformer part. Okay, so that's all for this video, and we'll be doing the next part of auto transformer in a next lecture. Okay.